Hi everyone, I'm Masoud Agassi, and in this video series we are going to learn about processes and threads. Whether you are new to this topic or want to understand it better, this series will explain everything in a simple and practical way. Let's get started. In the last two parts we learned about operating system responsibilities such as CPU and memory virtualization, the definition of processes and threads, process scheduling policies, and finally steps of a context switch. In this part and the next one, part 4, we will explore the most important challenges of concurrent programming that every software developer should be aware of. So far we have discussed processes and threads in the context of the operating system. But why should developers use threads in their programs at all? The first reason seems obvious: utilizing parallelism. If a system has multiple CPU cores and the problem or program solves can be divided into smaller jobs, using threads allows the program to run faster by using all the available CPU cores. Another reason is handling slow I/O operations. If a program must perform slow blocking I/O operations such as network requests or file reads, using multiple threads enables it to continue working on other tasks while waiting for the I/O operation to complete. And the last reason is shared address space. While processes can also achieve parallelism, threads are more lightweight because they share the same memory space. This makes it easier and faster for threads to communicate and share a state, making them ideal for concurrency within a single application. Now that we understand why threads are essential in our programs, let's explore some of the key challenges of concurrent programming that we might encounter. Determining the execution path. In traditional single-threaded programs, it's straightforward to follow the execution path. Typically, the program flows from top to bottom, entering each method recursively. However, determining the execution path in a multi-threaded program is much more complex. Let's examine this piece of code as an example. We have a typical Java class here with a main method. When the program starts, the operating system creates a process for it, which we refer to as the main thread. Inside the main method, we first print a line. Then we create two threads, passing a runnable named sidework to each. In Java, runnable is an interface that represents an operation or task. Here, sidework is the task we want each thread to perform when they start. Next, we start both threads by calling the start method. If we don't call the join method on these threads, the main thread will exit the main method, causing the application to close without waiting for the two threads to finish their tasks. By calling join, we instruct the main thread to wait for these threads to terminate before exiting the application. Finally, let's review the sidework runnable. It simply receives a name which we use as an identifier for our threads, performs a time-consuming task, in this case counting from 0 to 10 million, and then prints a line. Can you guess the output of this program? Which thread will finish first? If we follow the traditional top-down approach, we might assume that thread 1 finishes first, followed by thread 2. However, the actual result is different. Let's execute the program to see the output. In the first execution, thread 2 finishes first. In the second execution, thread 1 finishes first. And in the third execution, thread 1 finishes first again. It seems the execution order is non-deterministic. But why does this happen? As we have learned, the operating system's scheduler uses sophisticated policies to decide when to stop a process or thread and which process to switch to next. So, as programmers, we must assume that the execution context can switch from one thread to another at any time. For example, in this case, up to line 13, only the main thread is executing. At line 13, we start thread 1. Now the scheduler shares CPU time between the main thread and thread 1. After line 13, there are many possible execution paths. For instance, one possible path is that the thread 0, which is the main thread, executes line 14, starting thread 2, and then a scheduler switches execution context to thread 1, which executes the for loop in line 22 for 10 iterations. And then a scheduler switches to thread 2, which executes the for loop at line 22 for 12 iterations before the next context switch happens, and so on. Another possible path is that thread 0 executes line 14, starting thread 2. Then a scheduler switches execution context to thread 2, and let's say thread 2 executes the for loop in line 22 for 12 iterations. And then a scheduler switches to thread 1, which executes the for loop at line 22 for 10 iterations, and so on. Yet another possible path could be that after thread 0 executes line 13, a scheduler switches the execution context to thread 1, which executes the for loop at line 22 for 10 iterations. And then a scheduler switches to thread 0 again, which executes line 14, and so on. This non-deterministic behavior arises because the scheduler's decisions depend on many factors outside our program's control. Now that we have seen how the execution path of a multi-threaded program depends on factors beyond our control, let's explore another challenge that could make it even worse: shared data. Let's examine another program. This is a simple Java command line program. In this class, we have declared a static integer variable named counter. Inside the main method, after printing a line, we create two threads, each executing the side work runnable. Then we start both threads and call join method on them to make sure the main thread waits for these threads to terminate before moving to the next line. And finally, we print the final value of the counter variable. Now let's look at the side work runnable that both threads execute concurrently. After printing a line, there is a loop that iterates 10 million times, incrementing the counter by 1 in each iteration. What will the final value of counter be? At first glance, one might assume that since both threads increment the counter 10 million times, the final value should be 20 million. But let's run the program and see the output. It's a number around 12 million. Let's run it again. This time it's around 10 million. And if we run it again, we get another new number. Why we are getting these inconsistent results? Let's analyze the code to understand the reason. At line 27, it appears that we have a single increment operation executed by both threads concurrently. However, behind the scenes, this operation consists of 3 instructions for the CPU. First, the current value of counter is read from memory and stored in a CPU register. Then the value in the register is incremented by 1. And finally, the new value is written back to the memory address of counter variable. As said before, in multi-threaded applications, the scheduler may switch execution between threads at any point. This non-deterministic execution order can affect these 3 operations as well. What could happen is that first thread 1 reads the current value of counter from memory, which is 0, and stores it in a CPU register. Then thread 1 increments the value in the register to 1. But before thread 1 can write the new value back to memory, the scheduler switches execution to thread 2. Then thread 2 reads the current value of counter, which is still 0, increments it to 1, and writes it back to memory. Now when execution switches back to thread 1, it writes its value, which is also 1, back to memory. In this scenario, both threads executed the increment operation at line 27, but the value of counter only increased by 1 instead of 2. Due to the non-deterministic nature of the scheduler, This issue can happen in some iterations of the loop, leading to the inconsistent results we have observed. We could prevent this issue if the increment operation at line 27 was an atomic operation. An atomic operation is a sequence of instructions that execute as a single unit. It is either completely performed or not performed at all. We explain the classes that Java provides to help with concurrency issues in the next part. But for now, let's say that Java has an atomic integer class that provides what we need, atomic operations on an integer value. Now let's change the type of counter variable to atomic integer. We also need to update the increment operation. Now those 3 units of work for incrementing the counter variable are replaced with only 1 unit of work. Let's run the program again and check the result. Yes, now we are receiving the correct number. It solves our problem, but please be aware that a sequence of 2 atomic operations is not atomic as a whole. To explain this issue further, let's add another counter to our program. We also want to print the final value of the second counter. And finally, inside the side work runnable, we will only increment the counter 2 if the value of counter 1 is divisible by 10. Now the expected final value for counter 1 is 20 million, and for counter 2 it's 2 million. Let's execute the program and check the output. No, the final value of counter 2 is higher than 2 million, and if we run it again, we receive a different incorrect value. Let's revisit the code to understand what's happening. We have an atomic increment operation at line 30, and then we have another atomic operation at line 32 to read the current value of counter 1. As mentioned earlier, a sequence of 2 atomic operations is not atomic as a whole. For example, what could happen here is that thread 1 executes the increment operation at line 30, but before thread 1 can execute line 32, the scheduler switches execution to thread 2, which also executes the increment operation at line 30. Now when execution switches back to thread 1, it reads the current value of counter 1 at line 32. But 2 increments have already occurred since the last iteration. To solve this problem, we need a lock mechanism that ensures only one thread can enter a critical section of code at a time, while other threads wait. This is exactly what the synchronized keyword in Java provides. To use a synchronized block, we need a lock object. A lock object is any immutable object that controls access to a shared resource. Let's create one now. Now let's place the critical section of code inside the synchronized block using this lock object. It's worth noting that we can use any immutable object as a lock. In Java applications, it's common to use the class object as the lock for static resources. For now, let's use our own lock object. Now when a thread reaches line 31, it first checks whether the lock associated with the synchronized block is already held by another thread. If the lock is free, the thread acquires it and enters the synchronized block. Once the executing thread reaches the end of the synchronized block, it releases the lock, making it available for other threads to acquire. This mechanism ensures that only one thread can execute the code inside the synchronized block at a time, while other threads must wait for the lock to become available. By using this synchronization approach, we guarantee thread-safe access to the shared counter variables. Since the synchronized block now handles thread safety, we no longer need the atomic integer class. Now let's run the program again to see the result. Yes, now we are receiving the expected value for the counter 2 as well. Thanks for watching part 3 of this tutorial series. In the next part, we will continue this discussion by exploring 3 more challenges of concurrent programming. It's going to be an exciting journey, so make sure to stay tuned.